Okay, so here we're going to look at something new called rational expressions, as you can see. And just like from integers, you can form fractions of integers, that is, you can form rational numbers. Rational expressions are similar, except instead of starting with integers, you're starting with polynomials. So as you can see here, by definition, a rational expression is just a quotient of two polynomials. In other words, it's just one polynomial divided by another one. That's really what I'm trying to say over here. You know, you have two polynomials, p of x and q of x, and you just have one divided by another one. So it's a fraction of polynomials, so to say. These are just some easy examples. You have 1 over x. We have 1 over x squared minus 1. You have x squared plus 4 over x to the 5th plus 3x to the 4th minus 2. You know, these are all examples of rational expressions. You might have seen these already in the course. And if you didn't, that's okay also. Notice, just like any integer itself is a rational number, any polynomial itself is a rational expression. That should be expression. Let me just fix that. Mostly because when you divide by 1, you're not really doing anything, you're not getting anything new, so to say. Right? If you take p of x, for instance, p of x divided by 1 is just p of x. That's all. Now, when are these defined? Well, we know you never want to divide by 0. So rational expressions, they're defined, that is, their domain is all numbers except the ones that make the denominator 0. Here, I'm just writing this out symbolically. If you have a rational expression, p of x over q of x, its domain, which is the same as saying all numbers where the rational expression exists, is defined, that is, it's all numbers x except where the denominator is 0. So all x such that the denominator q of x is not 0. Same thing. And just like with fractions, you can simplify them, write them in lowest terms. You can do the same thing with rational expressions. We can actually simplify these. And we say a rational expression, by definition, is simplified if the numerator and denominator have no common factors other than 1 or negative 1. So it's really just like with fractions of integers, that is, right? It's in lowest terms if it has no common factors other than 1 or negative 1. Here, same idea. Okay, so based on that, you could probably guess how you would actually simplify a rational expression. It's also right here, the process. You factor the numerator and you factor the denominator, and then you just cancel out any common factors. That's all. Now, we know that factoring polynomials can be tricky, but what's nice is we have this result here, and this is a very nice result. And you can see, and it says that the x minus a, right, this binomial, x minus a, it's a factor of p of x. P of x, again, is a polynomial, exactly when p of a is 0. Okay? To prove it, you would need division of polynomials, but that's a different story. But again, this factor is very nice. So it helps us determine if x minus a is a factor without actually having to factor p of x. We just see, is p of a equal to 0? So as an example, let's consider this rational expression. Notice I wrote here x not equal to negative 2. All that's telling us is we're assuming x is not negative 2. You can probably see why, because in the denominator, if x were negative 2, the denominator would be 0, which we don't want to happen, right? Because we never divide by 0. So if we want to simplify this, well, notice the denominator is factored already, right? For the numerator, well, let's see if we can factor that. Well, we can, right? Because if you look at the numerator, which is x cubed, right, plus 2 times x squared. Well, hopefully you can see that the smallest power of x here is 2, so we can factor out x squared. And how do you get what's left over? As we saw earlier in the course, you just divide. That's all. Right? You divide each term by x squared. Hopefully I'll fit this. Just write down here. So we have x squared, right? When you divide, you subtract exponents. So the first quotient is x to the 3 minus 2, which is just x to the 1. Here, the x squares are going to cancel, so you're just left with a 2. And of course, that's the same as x squared times x plus 2. So now this rational expression, right, what we're dealing with here, that's going to become x cubed plus 2x squared over x plus 2. This is going to be x squared times x plus 2 all over x plus 2, right? The x plus 2s, let me just change the color. These are going to cancel, so all we're left with is just x squared. So we simplified it. And again, we're assuming x is not negative 2, right? Because again, otherwise, the denominator would be 0. Okay, so here's another example. Now here we're assuming x is not 1, and we're assuming x cannot be negative 2. Because if x were either one of those two numbers here, then this denominator would be 0. And we don't want that to happen. So the domain for this expression is all x such that x is not 1 and such that x is not negative 2. So we're assuming x is any number except 1 and except negative 2. So anyway, we want to simplify this. Okay, so what do we have to do? Let's factor. So we have x squared. We're doing the top first, like so. Now here, notice that we have degree 2. We have 3 terms, meaning a trinomial. The leading coefficient is 1. So to factor this, right, we want two numbers whose product is negative 3, whose sum is 1. Okay, well, what numbers are going to pull that off? Well, hopefully it's easy to see. You get 3 and negative 1. Wait, let me see if I can make that look like a nicer 3. Like so. And so we get x plus 3 times x minus 1. And for the denominator, which is this, same idea, right? Again, we have a trinomial, okay? Trinomial, leading coefficient's 1, and the degree is 2. So just like with the numerator, we want two numbers whose product is the constant term, negative 2, and whose sum is the coefficient of this term, which is in this case 1. So what numbers are going to pull that off? 2 and negative 1, like so. And so we're going to get x plus 2 times x minus 1. Okay, now let's rewrite the rational expression. So again, we have x squared plus 2x minus 3 all over x squared plus x minus 2. Okay, so now let's write in factored. We have x plus 3 times x minus 1 all over x plus 2 times x minus 1. That's good. Now, okay, so are there any common factors? Well, yeah, we have x minus 1, right? So, canceling these, we get x plus 3 over x plus 2. And now, our rational expression is simplified.